we can now define an alternate set of state variables Z1 and Z2, where Z1 can be defined as y plus y dot and Z2 can be defined as y minus y dot. So if y is displacement, y dot is velocity or speed, we can even have different quantities having different physical meanings being resulting in state variables. So when we collect them, right? This is once again an example. We collect a new state vector Z with the column vector being Z1 and Z2. That can come as this transformation matrix T multiplying x1, x2. Okay. So the transformation matrix becomes 1, 1, 1 minus 1. Why? Because Z1 will be then x1 plus x2. Z2 will be x1 minus x2. Okay. So consequently, we'll have Z of t, the vector, to be t times x of t. Okay. So where t is a transformation matrix, which essentially maps the state vector x we started off with, right? So the state vector was the first choice, right, of state variables, and then we transform to z. Okay, so through this transformation, and in general, if we have z to be some t times x of t, we need this transformation matrix to be invertible. Okay, so that is non-singular. Then what we can do is that, like, if we consider the standard linear time invariant, we can consider do both the MIMO system and the SISO system. If we consider the multi-input, multi-output transfer function, sorry, not transfer function, the state space representation, where x dot equals ax plus bu, y of t equals cx plus du, and we take z of t to be t times x of t, where we took t to be invertible. So then we can get x of t to be t inverse z of t. That is, we can also invert the transformation matrix t so that we can get x of t to be equal to t inverse z of t. Okay, so this is also possible. So if we are able to do this, we can get a new set of transform state equations, right? So we'd have gone through the mathematics in the video, but essentially it's only one step, right? So where z dot is t x dot, and then like we just substitute for x dot, and then like we simplify this, right? So what we have is that the new state equation or the transform state equation is now gives the evolution of z. Okay, so our initial state equation gave us the representation for the evolution of x, whereas the new state equation or the transform state equation gives us an evolution for the state vector z. And we also have a transformed output equation, right, which tells us what the output is in terms of the new state vector z. Okay, so as we know, the set A, B, C, D is what is called realization of a system, right, in the state space representation. When you and I apply this transformation, we can immediately observe that the state matrix gets changed from A to TAT inverse. The input matrix B gets changed to TB. The output matrix C gets changed to CT inverse, and the direct transmission matrix D remains the same. Okay. So this is the transformed realization. Okay, this is the transformed realization. So like this, we can construct an infinity of such realization, right? Why? Because there's an infinite number of invertible matrices T, right, which can essentially help us go from X to Z, right? So that is always possible. Okay. So consequently, this is what we have, and this shows that, you know, like you and I can have an infinite set of state space representations, because each one of us can choose many such transformation matrices T, right? So that is why the state representation is not unique. Okay, so we can have an infinity of such transformations. But this operation of rewriting x in terms of z, where z is some t times x of t, and t is an invertible transformation, is what is called as a similarity transformation. Okay, why is it a similarity transformation? The reason is that the eigenvalues of A and T inverse are the same. Okay, this I leave it to the mathematically inclined amongst our class to show, but it can be shown. Okay, so you and I are only going to take the result, and the eigenvalues of the original state matrix A and the transform state matrix T inverse are the same. Okay, so that's why it's called as a similarity transformation. So the eigenvalues are the same. Okay, and the set of eigenvalues of a matrix is also called as a spectrum of a matrix. Okay, so for example, if we want to write what is called as a spectrum of the state matrix A, we use the symbol sigma of A. Okay, sigma is the spectrum of A, and that is nothing but the set of eigenvalues of the matrix. Okay, so this is the concept of a similarity transformation, and and essentially we have to be the same. Okay, for A and TATs. Okay, so given this, and the question is, when do we use such similarity transformations? Okay, so typically, as we know, when we deal with the state space representation, we need to use a lot of computational tools, right, and computational ideas. That is, we have this vector ODE which we need to solve, and by and large we use computational methods to solve it, right? And many times when we use similarity transformations, we'll observe that the algorithms for solving computationally also become simpler, okay, in structure. Okay, so that is the I would say advantage of using a similarity transformation. All right. Okay. So that is one of the advantages. Okay, not the only advantage, but we can get a simpler structure and maybe possibly easier computation, right? When we want to solve and analyze the state equations. Okay. This one can show that the eigenvalues of A and TAT inverse are the same. And from the perspective of our course, why do you think this becomes important? If we recall our discussion on stability, right? What was we are going to look at that shortly, but then what was the condition for stability as far as the eigenvalues of state matrix were concerned? For stability, all poles of the transfer function should lie in the left of complex term, right? What about eigenvalues? No.
So the lambda value should be negative if I'm not wrong.
Yeah. So the point is, when we look at the state space representation, stability is linked to the eigenvalues of the state matrix. Okay. So consequently, we will be looking at it shortly. Okay, like when we look at what is called as stability of an equilibrium state. So the eigenvalues of the state matrix and their location will dictate, right, what will be the stability of the system when we deal with the state space representation. This is an important result. Why? Because see, similarity transformation is just, we are just changing the state variables, right, for our convenience. But the underlying physical system is the same. So the physical system is either stable or unstable, right? Is it not? So just because I apply a mathematical transformation to change the state variables for some utility does not mean that the underlying stability of the system will suddenly get transformed, right? So we can see that that is indeed the case, right? So the eigenvalues will remain invariant, right? Depending on whether we are considering the older state matrix or the new state matrix or the transform state matrix. Okay. So one can once again show that the transfer function remains the same under the similarity transformation. This derivation just shows that the transfer function remains the same. Okay. So in summary, given a system and a model for that LTA system, right? Of course, right? Transfer function is unique, Okay, all of us will get the same transfer function, whereas state space representation is non-unique. Right, so that's what we have shown through this discussion. Okay, so I leave this to as an exercise for all of us to do. That is, now if we consider a CISO realization and we use z of t equals txt, please follow a similar process. This is not a homework, this is just an exercise for us to learn better. The state matrix A gets changed to T8 inverse. The input vector B gets changed to T times B. The output vector C gets changed to T inverse C, and the direct transmission term D remains D. Okay, and as we already know, the plant transfer function for SISO is C dot Si minus A inverse B plus D, and that remains the same. Okay, even when we do a similarity transformation. Okay, so that's the advantage of, or that's the result, like with a similarity. Okay, so I hope the notion of similarity transformation is clear, right? So as I told, the utility is you and I can apply these transformations to get the the state space representation in some preferred forms, right? Such that like we are able to do the computations and analysis in a simpler manner. Okay, so that's one advantage of using a similarity transformation. Okay, so I hope the concept of similarity transformation is clear. And please note that even though we essentially apply the similarity transformation, the eigenvalues of the original state matrix and the eigenvalue of the transformed state matrix remain the same. Okay, point number one. And the second point is that the transfer function, right? The plant transfer function is unique. So it doesn't matter what similarity transformation we use, the transfer function of the system, we have shown that will remain the same, okay, irrespective of the similarity transformation that is used. Okay, so these are two important points. Okay, so then let's go to the next important concept. Okay, as we have been discussing throughout this course, when we do control design, right? So it doesn't matter whether it is in the transfer function representation or the state space representation. Always there are two aspects that are important, right? Stability and performance. Okay, so in terms of stability, we have already looked at this notion of Bibo stability, right? So what was the criteria for Bibo stability?
The pole should lie on LHP.
The poles of the system transfer function should lie on the left of complex, right? So that is the condition for Bibo stability. Now, with the state space representation, we have another notion of stability, what is called the stability of an equilibrium state, right? So for that, first we need to understand what is an equilibrium state, and then we essentially look at the notion of stability of an equilibrium state, right? So we are dealing with the state space representation. Let's say we consider the state equation, which is x dot equals ax plus bu. Now, a state x star is said to be an equilibrium state if we essentially perturb the system from x star, it remains around the state x star. Okay, that is when the equilibrium state is stable. But to begin with, the definition of the equilibrium state is that a state x star is said to be an equilibrium state if the system will remain at that state forever, right? Unless otherwise there is some external input, disturbance, or perturbation. Okay, so let me give an example. So we take the simple pendulum, right? Let us say I hang a ball from the ceiling using a thread, and there is no disturbance. Let's say no wind, no airflow, nothing in the room, right? So what will happen? This pendulum will be vertically downward, right? So it will hang vertically downward due to gravity, right? So this is an equilibrium state. That is, the pendulum will continue to remain in the state as long as you and I are not going to give any external input or perturbation, right? I hope that is clear, right? So if you have, let's say, suddenly I turn on a fan in the room, there may be some wind flow, right, due to which the pendulum may start swinging a little bit. So suppose if I tap the pendulum a little bit, that's a perturbation I'm giving. Then the pendulum may start swinging a little bit. But in the absence of these external inputs or disturbances or perturbations, the pendulum will continue to remain vertically downwards. Okay, so nothing else is going to change that. So given that, how do we formalize an equilibrium state, and then only we can look at stability of equilibrium state. So using this definition, so if you and I look at the state equation x dot equals ax plus bu, what is the definition of the equilibrium state? The state starting x star remains at x star. So what do you think will be the time derivative of x if my state is at x star? It is going to be 0, the 0 vector, right? Why? Because if the state is going to remain at x star, right? If the state of a system is going to be at the same value for all time, right? What is the time derivative? 0. Correct? Is it not? Because if some quantity does not change with time, that derivative is going to be 0. And it will remain at that state in the absence of any external inputs, perturbations, or disturbance. That means u is also 0. So what will happen to this equation? The left-hand side is 0. The second term on the right-hand side is 0. So what do you think will happen to this equation?
Equal to 0.
Yeah, left-hand side is 0. So we'll get ax star to be equal to 0. Right? Why? Because there are 3 terms, right? Let me call it as 1, 2, and 3. Terms 1 and 3 are 0, right? So term 2 should be 0. I hope it's clear, right? So what is term 2? The state matrix A multiplying the state vector x. In this case, we are replacing x with x star because that is a symbol used for the equilibrium state, right? So you and I are trying to figure out what the equilibrium state is. I hope it's clear how we got this, right? So let me repeat once again. The state equation is x dot equals ax plus bu. Let us say, we are considering this pendulum, and you and I want to figure out, at what state it will continue to remain in the absence of any inputs or disturbances or perturbations. That's an equilibrium state, right? So to calculate the equilibrium state, x star, we are just putting a star over x just to indicate that it's an equilibrium state. Okay, so x is the general state. Okay, so x star is a particular equilibrium state. Okay, so that is the notation that we are following. Now, what happens is that we are essentially having x to be equal to x star means x star becomes 0. And since u is also 0 because there is no external input or perturbations, terms 1 and 3 in this equation becomes 0. So the solution to ax star equals 0 becomes the equilibrium state, right? Becomes a possible equilibrium state. I hope everyone agrees, right? Is it clear to everyone how we got ax star equals 0? So now, what sort of quantity is A? Scalar vector matrix.
Scalar.
A.
It's a matrix actually.
A is a state matrix. Okay. It is filled with constant entries, okay, for an LTA system, but it's a matrix, right? If you remember the state space representation, it's an n by n matrix, right? Where n is the number of state elements, right? What is x star? What sort of quantity it is? Scalar, vector, or matrix?
It's a vector quantity, sir.
It is vector. So what we are saying is that we have a matrix multiplying a vector, and that is equal to a 0 vector. Okay, correct. So that's what we have this. So we have a x star that is equal to 0 vector. Now, from matrix vector algebra, we know that if I have this such an equation, right, where ax star equals 0, where A is a matrix, x star is a vector, and the product of the two is a 0 vector, there are two choices, two solutions. Okay? So this can be shown. I'm only using the final result, okay, in this particular process. Okay, so if A is a non-singular matrix, okay, so that means that it's invertible. Okay, so if A is a non-singular matrix, that means it's invertible. Then what happens is that the only solution for X star is that it is the zero vector. Okay, so X star equals 0 is a unique equilibrium state at the origin, right? So an intuitive way of explaining this is that suppose, let us say A is invertible, so X star will become A inverse 0. So any non-zero matrix multiplying the zero vector is also 0. Okay, so this is an intuitive way of explaining the same thing. So you can immediately see that X star becomes equal to 0. Okay, so we have a unique equilibrium state at the origin. All right, so that's what happens. Right now, if the matrix A is singular, okay, so that means it is non-invertible, then X star belongs to what is called as a null space of A. We will not worry about these details, but I'm just giving you the fact, okay, as far as this result is concerned. Okay, so we can have the state matrix A to be also singular. That means we are not able to take the inverse of that matrix. Then what we have is that, like, we'll have a infinite number of equilibrium states, which will be a what is called as a continuous set of equilibrium states, which belong to a so-called null space of the matrix A, right? Because you mentioned that you are yet to take a computational course, right? Am I correct? If I remember from last week's discussion.
Yes, sir. Yes, sir. It will come in next sem.
Next semester, right? So typically in a computation course, you will learn a lot of matrix algebra, and you also told that you have not taken the what to say, this one, right? Yeah. A linear algebra course or a matrix algebra course, right? Yeah. Am I correct?
Yes, sir. It has not been like taken up.
Taken up, right? So consequently, that is why you will be learning it. I'm just using an what to say, useful concept from it. Okay, so that's all there is. So so if A is what to say, singular, then X star belongs to what is called null space of A. See, what is null space of a matrix? A null space of a matrix is all such vectors such that A times X is 0. Okay, so this is the definition of null space of a matrix. Okay, null space of a matrix A. So if A is invertible, null space is 0. Okay, it's only the 0 vector. But if A is singular or non-invertible, then we have an infinite set of vectors, okay, which belong to the null space of A. Okay, so that is the result. So for our example, we will have, or for our dynamic systems, we'll have an infinite set of equilibrium states when the state matrix A is single. All right. Okay. So we'll be doing these two exercises tomorrow, but you can try them out. So I have given two second order systems where in the first case, the matrix A is 1, 3, 1, minus 2. In the second case, it's 1, minus 3, minus 2, 6. Okay. So please find out whether what is the equilibrium state in each of these two cases. Okay. So you'll see that in one case, the matrix A is invertible. So consequently, the origin is the unique equilibrium state. In another example, we'll find that the state matrix A is singular. So consequently, we'll have an infinite set of equilibrium states. Okay. So please try them out. We will do this example in the next class, right? And by the way, tomorrow you will be meeting with Abhinav, right, for the help session on the project. Our next theory class will be on Wednesday. Okay, so on Wednesday we will look at these two examples, and then like we will look at go ahead and look at stability of an equilibrium state. Okay, fine. So this is what we have learned in today's lecture. Any questions on these concepts? So we have broadly looked at two important concepts, right? So one is the idea that there exists an infinite number of state space representations for a given system. We have understood it through similarity transformations. Okay, so that's what you and I have done. Point number one. Then, what we have done is that we have essentially looked at the definition of an equilibrium state. The definition of an equilibrium state is one where the system will continue to remain, right, in the absence of any perturbations or things. Okay, so that is what will happen within equilibrium state. Okay, these are the two main concepts that we have learned. So any questions on them?
Sir, am I audible?
Yes, please.
So I just couldn't help but notice this second option where A is singular and then X star belongs to the null space of A. That example below where you have worked out, that option becomes X star equal to, if you can slightly scroll down.
Hello, Prem, scroll down. Okay.
Yeah, so what I'm able to see here in the second example is that X star becomes C times 3 into 1. So what I'm trying to understand is this becoming like a scaling kind of a option?
So essentially what it means is that, Prem, is that C, you can think of it as a scaling factor, right? But C can be any real number, right? Is it not?
Yeah.
Okay. So there exists an infinite set of equilibrium states from that perspective. Okay. So that's what you and I are able to conclude.
Yeah. So
Okay?
coming back to the question now. So if that is the case, when it is getting scaled, then how can each scaled value be an equilibrium state?
Because if you do this, right, in the second example, right? So what is the definition of an equilibrium state? Ultimately, mathematically, AX star should be 0, right?
Correct.
So if you have 3C and C, right, you take the product, what do you get?
Yeah, mathematically, I'm able to understand. Yeah,
Zero,
it's
zero.
going to be
So physically, what happens is that like any frame will direction will continue. So that is the physical.
If I take the example of that fan speed that you were saying, so if I change and explain if it's possible.
Which fan speed?
Sir, you mentioned one example where in case of the pendulum, wherein we increase the fan speed and then the pendulum oscillates.
Oh, okay. Yeah. So in this case of a simple pendulum, okay, there is only a unique equilibrium state, which is the vertically downward state. Okay, so it doesn't have an infinite set of So what did I mean by fan? I wanted to give an example. What is the perturbation, right? Yeah. So imagine that in the room that you and I are sitting, right? We take a string and then we tie a ball and we hang the ball, upside down, right? What happened? That's a simple pendulum, right? Is it not?
Yeah. Okay.
So now, if we just start the fan in the room, right? What's going to happen?
It will start oscillating.
It will start oscillating. Why? Because there is going to be a perturbation in the form of some airflow.
Correct.
Right? And that is what I meant. Okay. So, all right.
Okay.
Fine. So, but then in the case of a simple pendulum, we have a unique equilibrium state. Okay. So that is the bottom line. But interestingly, when we go to nonlinear systems, okay, when the pendulum oscillation becomes significantly high frame, you can have what are called multiple isolated equilibriums. Okay, like we'll come to all those subtle things shortly. Okay.
So if I have to just
So to give an example, this is the vertically downward equilibrium state. Okay. So this we will say it's stable intuitively, right? Why? Because if I tap the ball, it's going to oscillate around that equilibrium state, right?
Yeah.
Now there's something called as an inverted pendulum. Imagine that you balance a pen in your palm.
Correct.
Right? So you have an inverted pendulum. Okay. So now the inverted pendulum is inherently unstable. Okay. So although it's an equilibrium state in the perfect world, the moment you and I have a disturbance, the disturbance can be due to the fact that our palm is not flat, right?
Yeah.
And
Yeah.
we may not hold the palm also horizontal,
Yeah.
right? So essentially, consequently, due to that, the pendulum may fall down. Okay, so that is the vertically upward equilibrium state, which is unstable inherently to begin with. Okay, yeah.
So the second example, meaning where we are talking about infinite equilibrium states, is more or less what happens in automotive dynamical systems. If I can,
Not necessarily.
not
Okay,
necessarily, but
not
yeah.
necessarily. So there are three things. Okay, so we'll discuss this in detail next class, hopefully. That is, we have a unique equilibrium state. We can have a continuum of equilibrium state like this. Okay, for linear systems, we can have only one of the two. Okay, that is point number. Now, when we have a non-linear system, okay, then we also have what is called as isolated equilibrium state. Since this discussion came out, Prem, I'm just sharing for the information for all of us
Okay.
that
Yeah.
this pendulum is a nonlinear system. Okay, you and I have isolated equilibrium state. That is, what do I mean by that? For a
We are
pendulum,
looking at
this
particular states only. Yeah.
this either this vertically downward equilibrium state, which you can call theta is 0 degrees, and vertically upward equilibrium state, which will be then theta equals 180 degrees, right?
Yeah.
Are
Yeah.
the only two equilibrium states, okay? Point number one, right? And they are separated. It's not a continuous. So we don't have any other value of theta in between to be an equilibrium state, right? Is it? Okay.
Got it.
So that is why they are called isolated equilibrium states. And
So a
that,
suspension spring oscillating in between, and the top portion and the bottom portion could be the isolated equilibrium states.
well, I wouldn't visualize like that, Prem. Okay, so isolated equilibrium states are characteristics of a nonlinear system. Okay, so when you have a suspension, right, the question is what is the equilibrium state? So suppose, let us say, I manufacture my vehicle, I put it right, and it stays it stays on a road, and the suspension spring deforms due to the weight of the vehicle, right?
Correct.
So that initial state is an equilibrium state. What do I mean by that? If I do not now move the vehicle, right? If I do not jump up and down within the vehicle, right? Then the vehicle is not going to, the suspension is not going to deflect. Okay. But when you ride the vehicle, the suspension may go from its maximum deflection to minimum deflection. That's a separate thing. Those are not equilibrium states. Okay. Correct. Those are only limiting states of the suspension deflection. Okay. So what is an equilibrium state is only the initial state where you assemble the suspension and you have the suspension deform and stay there, as long as there are no other disturbances come or inputs come.
So I could have, so I could have compressed the spring as much as I had wanted for different equilibrium states and kept the car as it is without any disturbance. That could have been the case of infinite.
Yeah, exactly. But that's a natural state, Prem. See, what is a natural state? Depending on the mass of the vehicle, it will go to only one state.
Correct.
We may artificially add some 100 kilogram mass to the vehicle and then compress it further. Okay. Then you and I need to debate whether that's an equilibrium state, right? Because you and I have provided an external perturbation, right? Although constant. Correct? Yeah.
But it's a very clear.
What is the vehicle's natural equilibrium state? I assemble the vehicle, right? Whatever state it just settles down to, that is the natural equilibrium state. Okay?
Thank you, sir. Clear.
Yeah. Okay, the questions.
Sir, this class is a bit like I would say concept oriented, which is probably we'll try to comprehend and ask the question in next class actually.
Yeah. Please do, because I think we will have a few more lectures, Roshan. Most of it is going to be concept oriented, but then we need to learn these for us to essentially go forward with controlled design in the state space form. Okay, that's why we need to learn these concepts. Okay, yeah. And as I
Sure.
told, it is good that they are new and then we are thinking about it, right? Because if not, then we are not learning anything new, right? So, correct?
Sure, sir. Sure.
Any other questions?
Sir, just out of curiosity, sir, basically, do you have any NPTEL video on hybrid vehicle and electric motors and all those things, sir?
So there is a certification program on electric vehicles and also this web-enabled MTech in e-mobility, right? Those we have launched, but that's behind a paywall, Roshan, right? I also have lectures recorded as part of it, along with other colleagues, okay, who are all experts in various domains of e-mobility.
So, sir,
but
can you share the link? We can just buy it if we want to learn about that, sir.
no,
Please.
you need to participate in the program, right?
Yeah, yes, sir. Yes, sir. Yes, sir.
So one needs to participate in the certification programs and all to learn it, right? So essentially, the next batch of for the certificate program on e-mobility will start on July 1st. Okay.
Okay.
So that's when it will start. Okay. So 1 minute. Let me share the link on it.
Sure, sir.
I'm just sharing it in the chat box so that you can look at it. It is in the same code website. Okay, so that's where the web-enabled MTech and automotive technology is also listed, right? So what program we are all discussing, right? So we have launched a set web-enabled MTech in e-mobility, okay, from the Department of Indian Railway, and a lot of certification programs on various topics associated with e-mobility and electric vehicles. Okay.
Thank you, sir. Thank you so much for
in
this.
that you can look at the certificate program on e-mobility. I'm just sharing the link to cohort 6 in the chat box. That is the 6th cohort. It's a 6-month program, around 6.5 months, right? I coordinate that program, but then if you go to the website, you will see that there are a lot of instructors. Okay, there are 13 modules. I only teach the vehicle dynamics and control module, and that too only for 11 hours. Okay, very, very brief. Okay, because this entire program is very brief. We want to provide the learner with the breadth of the program. Okay, more than that. Okay, so the depth is what we are doing through these courses, Roshan. Okay, there, I would have just provided a broad overview. Okay?
Sure, sir. Noted, sir. Thank you.
Okay. Arunachalam, is everyone present today? No, sir.
Sir, actually, he is not in the MTA hall, but he is on the call. So everybody is present, sir.
Oh, everyone is present.
Yeah.
Okay, not everyone is present.
Hello, sir.
Yes, Arunachalam.
Sir, just I came out some urgent emergency, so now joined, sir. Sorry.
No problem, Arunachalam. I think updated on
Right,
80%. Then we will continue on Wednesday. Right? Please note tomorrow. Abhinav will take over and answer your queries. Kindly use that session. Even if you want to share code and get his clarifications, please make use of that session. Okay?
Sure, sir. Thank you, sir.
Then we'll meet on Wednesday then. Right. Thank you very much. Thank you. Bye-bye.
Thank you, sir. Thank you so much.
Thank you, sir.
Thank you, sir.